So today we are going to discuss energy harvesting and intermittent computation. In this video, my goal is to run a cryptographic program on harvested energy using the PowerCast setup. So a little bit about the PowerCast setup. We are going to power our microcontroller using the PowerCast setup called P2110B. This is a power harvester which is a radio frequency energy harvesting device that converts radio frequency to direct current. The P2110B receiver provides the harvested energy to our microcontroller. It converts the radio frequency to direct current and then stores it in a capacitor. When a charge threshold on this capacitor is achieved, the P2110 boosts the voltage to the set output. When the charge on this capacitor declines to the low voltage threshold, the voltage threshold is turned off. And this is how this power car setup provides or supplies energy in intermittent cycles. Once the capacitor is charged, it provides some output power, and when the capacitor discharges, it gives zero output. Now, the harvested energy is thus supplied in intermittent cycles, which resets our microcontroller every time the power goes off. Thus, we need to save the intermediate state to resume the execution correctly after every power cycle. So to do that, I have used the external flash memory connected on the Metro M0 Express development board. The external flash memory is a non-volatile memory which will store the intermediate state of my program, and once the power comes on again, we retrieve this information from the flash memory using SPI and start the execution from the intermediate state instead of starting it right from the beginning of the cycle. Now let's look at the code a little bit. Now, just to give a background, this flash memory communicates with the microcontroller using SPI communication. So the overall idea of this algorithm is to save the intermediate state in the external flash memory at the beginning of every power cycle and then proceed to execute the encryption function. This indicates that every time the power goes off, our counter will be incremented, which will make sure that our execution cycles are progressing towards completion. And after certain power cycles, our executions will be completed to execution. Now let's look at the code for a bit. Now I'm using the hash defined reset flash to reset the flash every time I want to test my code. So if the flash has some previous value stored at the address that I'm using, then I just reset it by I first uncomment this macro and upload the code to the microcontroller to reset any location of the flash. Then I comment this macro to to upload my original code which does the intermittent computation. Now I'm defining this macro called iters to 250 or any number of iterations that I want my encryption or decryption to run. So my encryption will run 250 if I'm setting iters to 250, and after my encryption is executed 250 times, my code has finished running. I'm using the Adafruit SPI Flash library, which is basically the SPI Flash library, which sets up the communication with the external flash memory using SPI, and we can then use its APIs to do our intermittent computation. Now, I'm using the address EDDR as 0100, which is the second page, which essentially points to the 256th memory location, and index is the variable that stores the number of iterations or the current iteration value, and index copy is a temporary variable which is equal to the index value. Now going to our void setup function, which is where our function begins. Now I'm writing my code in void setup because I don't want to erase and write to the flash in continuously, because writes and erases to the flash are limited. So they are limited to 10,000 times. So I'll just do it once, and once my execution is completed, this won't run in a loop. Now, first I use pin mode to set my LED pin as output. My LED is connected to pin number 13. Then I initialize the flashes using the flash.begin function. Now, I write the LED as low on pin number 13 before my encryption or decryption. This is because I want to indicate using the LED that my execution is completed. So after the run encryption decryption function runs and is finished, I turn the LED on, which will indicate that our execution has completed. Now, in the run encryption function is my main intermittent computation code and my encryption and decryption function. So in the beginning of this code, I first use the read buffer function to read the value which is stored in the flash. Now, to do this, I have provided the address from which the data should be read and the variable to which the data should be copied to. So the data at address will be stored in the index variable. Now, initially the flash is set to 255 after we reset the flash. So if it is the initial value, that is the index value is read as 255, we set the index to 0. Now I have I am checking the condition where if the index has already finished the execution, that is, if the index value is greater than iters, that means our execution has been completed and we can just return from this point. That is, the function doesn't need to execute any encryption or decryption further. Now, if that is not the case, then we move on to this part of the code where we increment the value of index, store the value in index copy, which is then stored in a constant buffer, and then erase the sector of the address. Now I'm dividing the address by the size of the sector. The size of a sector is 4 into 1024, which is 4096. And this is so because we need to see in which sector our address is stored, and then we erase the sector. Now, the reason to erase the sector of the flash is because we can't directly write to the flash. We need to erase the flash before updating the value. So we erase the sector and in which the address our address resides, and then after that we use the write buffer function to write a new value to that address. So this value stored in buffer is written to the address addr using the write buffer function. So this is where I stored an incremented value of the current index to the flash buffer. Now after that I move on to check if my index value is less than iterations, then I move on to do the test encryption or test decryption function. Now, after testing this before, I know that test encryption or test decryption function runs at least once before the power cycle goes off, and that is why we can use this algorithm. So, once our test encryption or decryption function is run, I move on and increment the counter. Now, I am sure that the power will go off right after the test encryption or decryption function has been run, or it can go off after a few iterations. But it is assured that the test encryption function will run at least once before the power goes off. So if the power goes off here now, we will come back to the setup function. It the pin mode will be set up, the flash will begin again, then we move on to the run encryption and decryption function. The only difference now will be that the flash.read buffer function will now read an incremented value of index. So if the value was 2 in the previous iteration, now it will be 3. And now it will start the test encryption, it will run the test encryption function from the value 3 instead of 0. And this is how we will run our intermittent computation the number of times we need our code to run, that is equal to iters. So if my iterations are 10, then I will require 10 cycles to finish my computation, that is 10 power cycles to finish my test encryption or decryption function. Now we can look at the output that I have stored. So this is the um, output for 10 iterations where I have stored the iters as 10. I compile the code and upload it on our board. Before doing this, I resetted the flash by uncommenting this macro. Now, after uploading the code, we need to disconnect our development board from our laptop and connect it and power it through our energy harvesting setup. So, so after uploading the code, I have connected the picoscope to the power of the board and the LED of the board. The blue graph indicates the status of the LED and the red graph indicates the status of the power to the board. Now we can see that once the board is connected to the energy harvesting setup, the power is on and off. The on is the on period, which is 3.3 volts, and the intermittent cycles show that the power goes off suddenly. And after 10 cycles, since the iterations are equal to 10, after 10 cycles, we will get the LED output as 1, which is indicated here. So this shows that after 10 iterations, the code doesn't execute and the code has been executed 10 times, and that means we have successfully done our intermittent computation because our LED is turned on after 10 iterations. The LED will continue turning on after the iterations because we do not go and move on to re-execute the code once it has been executed once. So yeah, this is the indication that our intermittent computation code is working. Now I have also tested this code for 250 iterations as well. Here, after setting the 250 iterations, I have also recorded the output, and we can see that the picoscope will show the power cycles, and these are approximately 250 power cycles because the iterations are 250. I'll just skip to the end to show the output, and we can see that the output after 250 cycles shows that the LED is turning on, and we can see that using the picoscope. So with this, I conclude this video by um, concluding that we have used intermittent computation to store the intermediate state of our cryptographic algorithm iteration number in the non-volatile external flash memory, which is connected to the Adafruit Metro and Zero Express board, and we retrieve this we retrieve the intermediate state from the non-volatile flash memory every time the power comes up, and that's how we progress towards the execution of all the number of cycles. And this can be used for any of the intermittent computations on any of the other codes if we are if we are connecting if we are sourcing the development board via a power energy harvester.